Okay, welcome everyone to today's CGD seminar. We are about to start. Today we have our speaker, Hien Bui, from ARC Center of Excellence for Climate Extremes at Monash University. She got her PhD from National Central University of Taiwan and then got her postdoc at CSU, and her interest covers a lot about tropical meteorology, climate extremes, variability, and today she's going to give us a seminar about something that she's really interested in. And without further ado, let's welcome today's speaker. Thank you.
So, thank you for having me here. I'm just have two small topics that I want to share with you in these presentations. So the first one will be about the stationary wave patterns and how it's impact on the wildfire occurrence. And the second one will be something slightly different about the soil moisture and how it impact on precipitations. So let's move to the first one. So before starting, I just want to acknowledge all of the co-author of the work. That's including my previous boss, Axel Timmermans and Chuni Lee from ICCP in Busan, South Korea. And also my postdoc advisor, Eric Maloney at CSU. Hien is just moving to Monash and started his postdoc. And also Hien and Sun Song also from ICCP. Jackie and Will, I think Jackie is just moving to NASA, and also Will is here at NCAR. So I'm really glad that I have a chance to work with some of them on this paper. So I think that you all know what the wildfire is. By definition, is on type of uncontrolled fire that can spread across the regions. And these fire can start naturally, like by lightning or by humans, and it certainly have a lot of impact on humans and economy and others. So this is the map that put together by NASA that's showing the size of the fire across the world during 2003 to 2016. So the dark red colors mean the very large fire. And the bottom is some photo that I took just in front of my apartment several years ago. So that's my first time experiment on the fire. So as you can see, there is a lot of smoke and the sun turned red. I think the fire at the time is last for more than a month or so, and yeah, that's something about the fire for my experiment. And the second thing that I want to let you on is about the stationary wave. So in the atmosphere, we have wave, and the stationary wave is a planetary scale wave that quite stationary during across the seasons. So which means the wave patterns during the winter time is quite different from the wave patterns during the summer times. And there's several variables that we can use to represent for such kind of wave. So for example, in the map right here that's showing the upper level hemispheric circulations, and that using the meridional wind speed, and you can see that they have a very nice structure of the wave number 6 patterns. And these stationary wave can be assessed by topographies or diabatic heatings, and it's transport heat, moisture, and momentums, and of course have a lot of impact on the regional climate. So in this work, we focus on the impact of stationary wave on wildfire occurrence, and there are two questions that we try to answer. So the first one is whether they have synchronizations between the wave patterns and also the wildfire occurrence. They have several previous work on the connections between the high pressure system associated with the wave and the wildfire. However, they tend to focus on the regional scale. And so we try to doing something for the global large scale. And the second question is how the global warming can affect on this relationship. So to answer for these two questions, we use the CSM2 large ensemble. And at the time that we working on this paper, we just analyzed 50 ensemble member, the smooth biomass burning simulations. And we comparing 30 years in the historicals and the SSP 370 scenarios and focus on the summertime in the Northern Hemisphere. Okay, so the first question is whether they have a relationship between the stationary wave and Wildfire occurrence. So to answer the questions, we apply the singular value decompositions on the wave and the Wildfire. So this is the map showing the first SVD. We explain for 90% of the variance. So if you first focus on the contour here, that's a stationary wave, and you see that they have some high pressure center over the eastern of the US and also in Europe and in northern of Asia, and the low pressure center located in between. Then if you look at the shaded here, which is the phi count output from the phi parameterizations in the models, we can see that they have some collocations for the positive phi anomaly and the high pressure center in the upper the atmosphere. So for example, you see that the positive phi anomaly on the east side of the upper level grid, and also the negative anomaly in the east side of the upper level trough. So they have some kind of collocations between the wave patterns and also the phi occurrence. So why they have such kind of collocations between the two? So we further examine the atmospheric conditions and also the land conditions 15 days before and 15 days after of the fire. So I think it's maybe hard for you to see, but the shaded one is the burn area, and also the vector is the 850 hectopascal wind. And in fact, they have some collocate between the fire areas and also the anticyclone over the regions, although it's not so clear in the Northern America. And we also examine the rarity humidities patterns and also the soil moisture. So the rarity humidities are the shaded. And the soil moisture here, I'm just showing the negative anomaly, which is the broad-hatching regions. So they also have the negative locations of rarity humidities is also at the same locations with the fire. And also the negative anomaly of soil moisture. And in addition to that, we're also looking into the precipitations and also the temperatures. So as you can see here, it's have a nice structure of the wave number 5, with 6 patterns of the precipitation and temperatures. So with all these, I think that it supports for our arguments about the impact of stationary wave on wildfire. Okay, so in addition to examining the connections of stationary wave patterns and the wildfire occurrence, we also examine the linkage between the persistence of high pressure day and wildfire. So in this plot, on the x-axis here is the consecutive high pressure days, and I divide using the just using the omega 500 hectopascal. So you have a descending motions, and this is the phi occurring index, which we do as a normalization of the phi count associated with the high pressure days and the total of the fire. And this is just the PDF of the number of the sample. So yeah, and different colors for the historical and the future. So from this, you can see that the longer the periods of high pressure days, the higher chance of fire occurrence, which is very obvious for the first 12 days here. But, and that's we think that very consistent with the change in the relative humidities, higher temperatures, and also the reduce of precipitations. But The interesting point here is that like after the 12 days around here, the fire tends to reduce. And I think in realities, we argue that's may because of you burn all the thing and you have nothing else to burn, so that's why it's reduced. But this is the models, and I'm not sure why it happened like that. So that's something that the caveats and open for discussion in the paper. So given the importance of the wave and also the fire, we try to see how it changed under global warming. So repeat the analysis for the SVD patterns, but for the future scenarios. And as you can see that the fire somehow tends to increase, but the wave patterns look quite similar, at least over the land regions. So we think that some other factors maybe really contribute to the increase of the fire rather than the wave. And so we do some literature reviews, and in fact, there's a lot of study about that, like because of the increase of dryness and the reduce of relative humidities in the future, or because of the weakening and shape of the storm track. Also, the expansion of high pressure system, the increase of lightning can also increase fire. And also study about the ENSO impact on the fire. And of course, the fire management, among many others. Okay, so that's just something that I'm showing you about the connection between the stationary wave and wildfire in the Northern Hemisphere, summer times. And we found some collocation and synchronizations between the two, showing at the schematic diagram here. And we also see that the persistence of high pressure conditions can increase the fire probabilities. And last thing about the global warming impact that can increase the fire, but probably due to the changing background conditions rather than the stationary wave. So the results have been published in this paper, so take a look if you are interested on this topic. Yeah, this is my first one. Should I just start to the second one, or?
Either, yeah, you can either take questions or you can leave the questions to the end.
Yeah, so do you have any question, or I'm just moving to the next one? Yeah.
Oh, of course, yeah. It's a really nice study. Thank you very much. The first question was, you said it very quickly. The first SVD accounts for 90% of the covariance between the fire counts and the wave and the circulation.
Yes.
That's kind of astounding. That's a lot. And then also, I think you did note that North America, the high pressure doesn't seem to go with reduced fire counts, so there must be something else going on there.
Yes. So I think that when we show in this one, there's something really hard to explain if you're comparing for these regions in the European and Asians compared to the Northern America only. There's not so clear patterns for the synchronizations in that, but I think we did separate and doing the SVD for just Northern Hemisphere only, or European, And in that case, the patterns look clearer for the synchronizations.
And then second question, just how is fire count computed in the model? What goes into that? And is it directly a function of temperature and relative humidity?
That's a good question. I think they partially prescribe the fire in the land first, and because this is the fire count and so the burn areas output the models, I didn't show the fire index that calculating, but for the sorry?
The fire, I guess I should get the mic.
Yeah.
Fires can be initiated from lightning, or there's a presumed rate of sort of potential human ignitions that is related to the population density of the where you are. And then they can suppressed based on also population density and GDP. But in terms of fire count, it's not atmospheric humidity specifically, if I'm remembering right, but it's either soil moisture or which is a proxy for vegetation water content. So that soil moisture is a trigger, wind is a trigger. There's several factors that go into it, but I don't think it's actually the atmospheric humidity that's going into it. But I have to go back and look at the equation. So, and not all fires will turn into a big fire either. So, there's fire count is one variable, but then the size of the fire is then also determined by environmental conditions through an equation that is assuming fires look like an elliptical thing, and again taking into account the wind and the other environmental conditions. So, maybe that leads to the question. If you tried to look at this in observations, or have you tried to look at it in observations, and the complexity of fire in the real world. And the model of fire is a set of equations which are trying to approximate fire. But the real world is, so much more complicated. I wonder if you've looked at the real world at all.
Yeah, we did. So, in addition to using the model output for the fire, I also calculate the fire index, like fire weather index. Like you say that we use some atmospheric variables to calculate, and also, comparing with the real observations for the fire. But the problem is that the real observation is not long enough, and we think that it's really hard to see and like compare it with the wave pattern. So it's not clear, and also the pattern is kind of messy, I think, for the real observations.
Dave, could you pass the mic?
Thanks. I was wondering if you could comment on any implications for predictability. If fire is linked to this kind of large-scale atmospheric mode, is that a large source of predictability on a particular time scale, or is it modulated by other things to make a more complex picture?
Okay, yeah, I think for the predictabilities, so particularly in this book, we didn't really look into that, but I think because of the time scale of the stationary wave and things, we can see something around in the scale of 2 weeks or 15 days of that based on those kind of conditions. And also for, this kind of thing, for the high pressure system, when you have high pressure and then the subsidence, so I think that we can see some potential for the prediction beyond that, I guess. Yeah. Is that? Thank you. Yeah, so thank you for the questions. So I'll just move into the second topic. This will be a little bit different because we moved from the northern hemisphere to the southern hemisphere, and also moving from the models to just satellite observations. So this work will examine the relationship between soil moisture and precipitation in Australia and using the CYGNSS observations. Again, just acknowledge one of my co-authors, so Isian from Monash, Steve Sherwood from University of New South Wales, Sydney, and Kim and Dietmar is also my colleague at Monash University. Okay, so soil moisture is just the water content, the surface. You probably all know about this. And previous study also report that the importance of the soil moisture on drought condition, heat wave, and other extreme. So the thing is that we are interested in is the connections between precipitation and soil moisture. And you know that they are kind of two way of connections. First is precipitation impact on soil moisture is quite easy and straightforward because when you have rain or something, the soil will get wet and vice versa. But the thing that we will look into in this study is how the soil moisture impact on precipitations. And particularly, we will focus on the daily time scale. It's like how the soil moisture today can affect on tomorrow precipitations. And this is to distinguish with the longer time scale, like the seasonal or a long-term trend on the relationship between the two. And I'll show you in the next few slides where and when the feedback occurred, whether it's a positive feedback or a negative feedback. And also we will examine whether the persistence of the dry or the wet soil moisture can affect on the stream, like the drought, fire, or flooding. Okay, just very quick about the satellite that I'm using. It's from NASA. It's called the CYGNSS, or the Cyclone Global Navigation Satellite System. This is quite new. It's just launched in 2016. So the data that we are using in this paper is just 5 years from 2018 to 2022. And it's covered most of the topics, and just in this one. The advantage of this satellite product is that it has a very high temporal and spatial resolutions, and it's not affected by rainfall. So we think that could be a good data to examine the connections between soil moisture and precipitations. Okay, so first let's take a look at the spatial and temporal distribution of the extreme soil moisture. So here I'm just showing you, like, this one is the very first 1 percentile of soil moisture. So it's a very dry soil moisture. And as you can see, the peak of driest regions located here in the desert regions. And when it occurred, the time scale, like this is the months, and you see that in the northern part, it mainly occurs in June or August, and then move further toward to the south. And on the right-hand side here is the extreme wet soil moisture. So it's 99 percentile of soil moisture. And as you can see, it's mostly over the eastern coastal regions of Australia. And when it occurs, that mainly early of the years in the northern, and again move further when it goes toward to the south. Because the satellite just cover from 38 degrees south to us, 38 degrees north, so we don't have the data over this region. So back to the main question is whether they have connections between the soil moisture and next day precipitations. To examine this, we use the multiple linear regression models. So we have two models. The first one that I call it the restrictive models. So basically, we try to do some kind of predict today precipitations based on information of independent variable yesterday precipitations. And the reason that we put the information of the past precipitation into this is to account for the persistence of rainfalls and also the autocorrelation between the two variables. And the second model is called in the full models. So basically it's the same as the first one, but we're adding the information of the soil moisture into it. So the difference of these two models will tell us about the impact of soil moisture on precipitation. Okay, so here's the result. So the map showing you the feedback between soil moisture and next day precipitations. And you have the cross-hatching show the significant areas. And the positive value means that when you include the soil moisture, the inclusion of soil moisture will increase the probabilities of precipitations. And the negative value means that the inclusion of soil moisture will reduce precipitation probabilities. And so we see that they have a very significant feedback occur in the northern of Australia. We also, because we only have 5 years of data, but we also try to separate into the seasons, like the monsoon and non-monsoon, to see how the signal look like. And in fact, the feedback is quite clear and looks similar during the break period. Our explanation is that the signal only clear in the northern part because in these regions, maybe the land and atmosphere coupling is more strong in these regions. And also the rainfall, the source for the precipitation is more from the terrestrial source. And that's why we have a clear signal compared to other regions. Although it's not significant and not clear because we think that the source of moisture, the source of precipitation come from the marine moisture. So that's why the signal is not so clear in there. So that we see some feedback between soil moisture and precipitation. And then the question is that how long do we need, how long will it take for the dry soil or the wet soil need to persist before the stream something happen. So let's look at the dry soil condition first. And so here on the axis here is the soil moisture intensity. So it's a very dry soil. So the 5 percentile here is the driest, and then moving 25 percentile. And the bar here is the another 5 weather index that typically used in Australia, the 5 danger index. And the black here line here is the drought index. And the thing that we use these two indexes here because the soil moisture is not the input for these two variables. So that can give us objective evaluations of how the soil moisture can impact. So what I want to highlight from this is that as you can see that if you have a very dry soil, then the condition don't need to last very long for the stream to happen. So very dry conditions, then maybe just 6 days for the index reach the maximum value compared to like 25 percentile, which not so dry, and this may take for more than 8 days for the index to reach the maximum value. And similarly, we also examine the wet soil conditions. So this is also, again, very wet soil, 95% and 75%. And we see how it impacts on the river discharge and runoff with somehow using two represents for the flooding. And as you can tell that how wetter soil can have a higher chance of flooding. But we also acknowledge some of the caveats because we just use 5 years of data daily. So it also can, the result can be impacted by the satellite quality. Also we think currently is maybe the best one. And other factors like the climate mode, ENSO or MJO can also affect. But again, this is a very short time period, just 5 years, so we didn't really get into. And hopefully when the data get longer, we will revisit the issues. Also, like in our linear regression models, we just including the past informations of precipitation and soil moisture, but certainly other factors like the wind or the humidities can also affect our predictions. Yeah, so again, just a summary that we use the CYGNSS, the new satellite observation for soil moisture to examine the feedback between soil moisture and precipitation in Australia. And we saw they have a positive feedback in the northern part, especially during the black non-monsoon periods. And we also see that they have the persistence of very dry or wet soil conditions can further increase the chance of fire or flood probabilities. Yeah, and this is the paper that just published earlier this year. For more details, if you want to. Yeah, thank you.
Okay, we can turn on the ceiling. Can we turn on the ceiling mic now? Okay, yeah. And also, could we put up the Slido website? The Slido website for the online questions. Okay. Well, we actually have a question online. Well, is this a question or? Yeah.
That's from the first part.
Yeah, related to the first part. Well, I think this is a guess about the reason why after 12 days, like the number of currents actually reduces. Yeah.
I'm not sure about this. So I think that when we saw that signal, we try, so the one that I'm showing you is that we average for the entire mid-latitude in the Northern Hemisphere. But I also try some smaller regions to see whether the signal will be different. But some still quite the same, it's just the amplitude is different, but still reduced, so.
I think we've already speculated before that like, maybe the reason is that like, it has already burned for a long time, so there's not enough fuel to burn, which is similar to what this proposes.
I think, yes.
Okay. Do we have questions in the audience? Yeah, go ahead.
I had a question about the second part. It's so nice to see the use of the new satellite data. So when you showed the soil moisture one day, or that extra information from the soil moisture, so this is controlling for persistence of the precipitation. Is that correct? This is the independent effect of soil moisture
Yes.
on precipitation?
Yeah.
Okay. And then what precipitation product do you use for this?
Oh, yeah. I didn't mention. We use the GPM precipitations.
I think it's really powerful to do this.
Dave, go ahead.
What is the temporal resolution of the satellite? You said it was high
I'm
frequency.
using the daily one.
It's daily, but is it more than daily, or is it?
Currently, I think that we only have the daily time scale for this. So.
Because you know, there's the question about the next day's precipitation, but often the question is for the same day, because it's like the morning conditions can kind of set up what happens in the atmosphere, and then it will rain on the same rain or not rain on the same day.
Yeah, so on the other quarter, and I also tried discussing this, and also the reviewer also asked this, because we do have a dyno cycle of the soil moisture, but because of the data that we have a daily resolution, so we are unable to examine that, but yeah. Not sure if we have other satellite products that have a high resolutions to look into this issue.
Can I ask, like, why not using another like soil moisture product such as SMAP, which is specifically designed for soil moisture detection?
Yes, that's it.
It has a longer coverage and also higher spatial resolution as well.
Is that the one from NASA?
Yeah. SMAP. Yeah, soil moisture active, passive.
I think that we also measure on that in the part that when the satellite doing the observations, the frequency that is not that high as the thickness one. So I think that's part of the reason that using this new satellite is have an advantage. But yeah, that's also one thing to try because it's have a longer time period. Yeah, thank you for that.
Okay, and back.
So I think this is related to Claire's question, but can I see the equations again? Where like the precipitation of your previous day, and then so have you also done any tests where like your precipitation is only based on soil moisture for the day before, or do you always want to include the precipitation of the day before as well? And I guess I'm curious why that would be the choice.
You mean why I'm putting the previous day precipitations? Is that your question?
Yeah, as opposed to say, Model 3, this imaginary Model 3 would be based just on yesterday's soil moisture and then not include the persistence of precipitation.
Yes. So I think the reason is that we add in the past information. So actually we did several sensitivity tests. So here I'm just including one day, just yesterday. But we did some other that include up to 4 days before the event and see how. But there's not, the signal is very small for that, so we decided just use 1 day. And the reason that we put in the past information of precipitation is because, as you probably see, that the precipitation tends to last. It's occurred today and it's also occurred the day after. And if it occurred today, then it will wet the soil. How can we say that the soil here is causing the precipitation the day after, or it's just a system of precipitation occurs? So that's the reason that we add the information of precipitation in the past. And so, so that's why the difference of these two will just only from the soil moisture impact.
Okay, that makes more sense.
Yeah, thank you.
Yeah, go ahead.
Do you have a sense of if this is from evaporation or transpiration? Like what's driving this?
Yes, that's a good question. I think for the land and atmosphere coupling process, the evapotranspirations, I think, for the moisture source in the northern part, and that's why we have a clear signal in here. So
Both they're driving it.
evapotranspiration. Is that your question?
I was asking, do you have a sense of one, if evaporation or transpiration is like the stronger driver in this case, or maybe it's more?
I guess it should be the evapotranspirations, the later one. Yeah.
Okay, thanks.
Yeah, there is a comment online. So it seems like it has both the 24-hour and 6-hour soil moisture product. So you can actually do sub-daily soil moisture analysis.
It's a good news. Yeah, I will revisit this using this to see how. Yeah, thank you for that. Yeah.
On these timescales, are the feedbacks expected to be mostly local, or do you think there's a non-local component?
So I think based on it, we only see the strong signal in the northern part. So it's, I guess it's kind of local.
I guess I'm wondering, would soil moisture in one location affect precipitation in an adjacent location?
It's kind of hard to tell, but I think it's just a regional, like in that grid scale, I think.
Yeah, I had a related thought. It could be powerful to look at the circulation with and without, or with this multiple regression, linear regression model to see if, what sets up the previous day's precipitation is probably some presumably unstable synoptic conditions. And then the part of the precipitation that is actually responding to the soil moisture might not have that same kind of circulation pattern, or maybe there's something downstream. So that could be a nice physical insight.
So like adding some more independent variable into the equation.
Yeah, I'm not quite sure how to do that.
You could use
Synoptic
like a linear inverse model type framework where your state is both the precipitation and the soil moisture. And so then if that's like a multivariate in space version of this kind of regression problem, and you could see how one impacts the other.
Okay, thank you.
Yeah, I mean, Meg could tell us all about this, but the sort of evidence is that the atmospheric state, there's some days when it's most likely that the atmosphere is sensitive to what the land is doing, and there's other days when it's not. So it's either the circulation or the profile, and it's a fairly complicated, set of conditions which will lead to it. So often you're sort of having to do some sort of conditional analysis of when the atmosphere is sensitive and not sensitive. This is saying in the longer time period, averaged over many days, it's showing up as dominant there. But it could be that if you looked at the other parts around the world and around Australia, you might find certain periods or certain days when it was actually showing some sensitivity, and others it's not. So, but it's hard to do it just a soil moisture data set and a precipitation data set because you don't have enough information.
Go ahead.
Thank you. I wonder about the non-monsoon versus monsoon time. am I right with my intuitive interpretation that in the non-monsoon time, this northern region is more sensitive to soil moisture because it tends to be more soil moisture limited in that time? So evapotranspiration might be soil moisture limited?
Yes, yeah, good question. It could be one case. But I think like during the non-monsoon that the monsoon can bring the moisture from the ocean into the land, but we don't have that part. So it's just the local source of the moisture from the land, and so that's why the signal is stronger. Yes, it could be like what you said.
Okay.
I guess.
Okay. Well, in addition to like the like local response between soil moisture and precipitation, we also know that soil moisture has a relatively like long memory, right? Which can last for about like a few weeks or even like a few months. And there has been some literatures about like subseasonal to seasonal predictability of the soil moisture on the precipitation. Have you thought about like maybe you can extend to like a subseasonal time scale to look at the relationship?
Yes. Yes. I did. Yeah. Yeah. Actually, yeah. One of the thing that I planning to follow up with this work is to doing some for a longer one, like a seasonal longer time scale. Yeah, and that's also the reason that I visit here. Yeah, to talk to people and also looking into the model's point of view of this kind of relationship because it's just a satellite thing. So yeah.
Any like hints or like results so far?
Not yet.
Oh, okay.
Yeah, but yeah, looking forward to talk to people here. Yeah, while I'm here until middle of April.
Okay, right. Do you have other questions from the audience or online? If not, we can actually end earlier today because our speaker has a relatively succinct presentation for us. And if you have other questions, please go to the speaker. Yeah, thank you so much. Also, we don't have seminar next week, so yeah, I'll see you in 2 weeks. All right, let's finish.